Okay, good morning. Welcome back. Is the volume okay or too loud? No? Okay. Yeah, so my name is Konrad Viebahn and it's great to be here. I work at ETH Zürich. Thank you very much to Gediminas and Magena and colleagues for organizing. It's really a great workshop. A little disclaimer, so the multi-component for me will mostly mean two, but there will be one moment in the talk where it means three, so something to watch out for. The title of my talk is Bridging Analog Simulation and Digital Computation in Dynamic Optical Lattices. And what that means hopefully will become clear. In a nutshell, we've been using digital gates and digital evolution to enhance the capabilities of quantum simulation experiments. And the key novelty is the realization of very high fidelity collisional gates. You can imagine atoms, qubits in a lattice, and we've pioneered a way how to move these atoms through a lattice, overlap them to make a gate operation, and turns out that these gates can be extremely high fidelity and very robust. And the main story of today will be how to use these gates to basically have in a simulator, Fermi-Hubbard type simulator, additional capabilities with respect to which states you can engineer and which kind of observables you can read out. I'd welcome you to ask questions during the talk as well, so I'm very happy to discuss and yeah, at any time. So I'd like to start with a little bit more broad footing, since this is a conference on quantum simulation. I think I'll go even broader and say quantum simulation and quantum computation are kind of within the class of quantum processing. What do I mean by that? I mean a machine, a quantum machine, which many of us experimentalists are trying to build, and the theorists are trying to create schemes for these quantum machines where you can prepare some state. You have, in the broadest sense, you have some evolution. Mostly we want unitary, but we might even relax that. And in the end, we do some measurements. So it's a quantum machine where we can ask questions and get answers. And hopefully, in some years, of course, these answers will be, or these machines will be more powerful than just our classical machines. Okay, and within this framework, we have, of course, quantum simulation, where in most cases, we have like some kind of analog evolution, for example, optical lattice, which gives us the Hamiltonian. We prepare some state, we do something in the lattice, and then we read out. On the computing side, it's more or less the same story, except that our evolution is now decomposed into digital gates, and it can be universal. So you can do any unitary evolution, which means you can also simulate any a system that you want, which is, of course, nice. And then in the far future, which I'm not going to talk about today, but of course I think we have to keep in mind where this quantum processing is guiding us or leading us. We want, of course, our machines to be reliable and like the answer that we ask for these machines to be trustworthy. And for this, I really believe we need some kind of way of integrating measurements inside our processor. But this will not be the part of today's talk. Mostly these two parts and how we can integrate them further. Now, the simulation has the huge advantage that we have the Hamiltonian, and this evolution in time with the Hamiltonian, for example, is something that's very hard to do classically. So this is very powerful. However, so far, the amount of states we can prepare in these machines is kind of limited. Very often we have only access to thermal states or maybe some uncorrelated product states, but it would be interesting to have a bigger toolbox here for this state preparation. On the universal processing side, we do have access to arbitrary states and Hamiltonians, but then we have errors, and we also are less efficient. For example, if you want to do time evolution, you have to discretize everything in gates, and then we have like some trotter error, and it becomes very lengthy, and so on. So there is something to be said for both approaches, I would say. Okay, so far to the introduction part. Let me now introduce our platform. So I'm an experimentalist. I work with optical lattices, and we have a three-dimensional optical lattice. all the physics I'm talking about today is along this one direction. So we freeze out the transverse directions, and we have one-dimensional lines or tubes where we can do the physics. And the main kind of ingredient that we came up is a more industrial way, so to speak, of moving particles around. So this goes under the name of topological pumping, which we didn't invent. There were beautiful experiments before in the Takahashi group and also by Emanuel Bloch and Monika Eidelsburger. So a topological pump is something where you can move atoms through a lattice, or electrons, or anything really, maybe even excitations or phase transitions. This pump is a very powerful thing, and you can imagine it, the easiest way to imagine it is on a bipartite lattice with two atoms per unit cell. And this lattice is not static, but dynamically changing in time. Okay, so this is key. We have these A and B sides, and by dynamically changing this landscape, we can move the lower orbital here adiabatically to the right. So this is the ground state, will be connected to a symmetric double well configuration to the right, whereas the excited orbital is moving in the opposite direction because it's adiabatically connected to the antisymmetric orbital. Okay? So this is basically the key idea of this topological pump, where you have the ability by turning, let's say, a crank of a Hamiltonian, moving these atoms, and not just in one direction, which would be kind of classical, just boring kind of movement because there's nothing relative happening, but quantum in the sense that the quantum state you're in, defines the direction of movement. And by quantum state here, I mean external motional state. So this pump would be operate far off resonant lattice, so it's not state dependent, not spin dependent. So it means that you can put here a spin up or a spin down, and they get pumped regardless of the spin state. And in the experiment, basically, our innovation was to realize a lattice where we have imbalanced lattice power coming on this axis, so we have more light here than on the reverse path, and this allows us to do this pump in a very simple and robust way. So mathematically, we describe this in a language of Fermi-Hubbard. So we have on-site interactions, two spins, potassium-40. We can tune the interactions. And then we have the lattice parameters, the tunneling T, and we have a weak bond and a strong bond. And the strength of the bonds, the difference characterized by this delta, this dimerization parameter, whereas the side offset, the bias, so to speak, in the double well is characterized by this large delta. And here you get maybe a glimpse of why it's called topological, because if you now look at this dynamical modulation in time, you find a closed loop in this parameter space of delta, dimerization, and side offset. For the experts, now if you do a charge Berry phase map of this plane, you will find here a phase winding. So if you enclose it, you will get this quantized pumping, and if you choose a parameter loop which is not enclosing it, you will find stationary atoms, essentially. So, of course, the connection to topology goes a lot deeper, but for today, I think this suffices as a kind of intuition. Okay, so how well does it work, and how can we see that in experiments? These are some images. Each horizontal slice is a snapshot after different times. So here this is a time axis. We start off with 50,000 fermions loaded in the ground band of this lattice. And you see clearly that all the atoms are moving in one direction. So we populate the lower orbital here. And if you fit a slope, the slope is consistent with unity, essentially. Although we are actually pumping up a harmonic hill. So this shows you already that this topological pumping is quite robust, does not depend on like local disorder or a little bit of confining potential. It just keeps moving with the same velocity. Then a surprise happened. We were doing these experiments, and we thought, yeah, what happens if we just pump on and further and further? And I won't go into too much detail here, but the experts maybe appreciate that we have here actually a topological transition from our harmonic trap. So in the middle we have these churn bands moving, and then as we go outside, the local potential shifts this trajectory upwards until it does not enclose anymore the topological point. And we have here some topological trivial regions outside, and with bulk boundary correspondence you can then see that there must be an edge state connecting these bands. And this edge state basically leads to atoms reversing into the top band and pumping quantized in the other direction. So this phenomenon, I think, might be useful later on if we are thinking about using pumping for quantum computing and so on and so forth. Okay, but let's come to the gates. As I said, like, this pump is a very powerful tool, and we realize that now if you initialize atoms not moving in one direction, but moving in two directions, like initialize one moving right and the other moving left, they can overlap. So this is going a little bit away from the kind of condensed matter band picture where you're trying to fill bands and so on. This is really like local atoms sitting in a lattice with deep confinement here so they don't disperse. And these localized atoms are pumped towards each other. And then when they overlap, they make these gates. Okay, and just like a very brief overview of this gate operation can be understood on the single double well, really, because again, these orbitals, they have some history. Let's say this might have moved from the left here, this might have moved from the right, but the gate operation can be understood on one double well. And key here is that we have this overlap between the wave functions, which, as another twist to the story, is not necessarily perturbative, but can be first order. So we don't need to go in the Heisenberg regime to get an effective spin-spin interaction. So this was basically one of the insights that we had from this project, that you have direct wave function overlap, which makes the gate more robust. And how do we measure this in the end? So we prepare some kind of state which is sensitive, in this case, of a swap to the swap gate. This is our measurement technique that will also become important later. So it's called a singlet-triplet oscillation. We have a gradient that we apply on our double well, and by merging the double well, we can map out singlet state. And if we now then do a dynamical evolution with this gradient, we can induce a splitting between up-down and down-up states and realize this oscillation here. Essentially, you can think of it as a parity oscillation. And this means this is our starting state. This is just the kind of the oscillation that we have before the gate. And after doing one of these gates, the oscillation is flipped, which means that we introduce this minus sign from the gate operation. And what's remarkable here is that these gates are happening in parallel. So we have 30,000 atoms doing this in parallel, and all of them are doing this coherently, and we get already 3 nines of fidelity if we correct for state preparation and measurement. So this is the gate. I would have to also say that there were some very nice results in parallel in the Munich group, in the more Heisenberg regime, and also from Janwei Pan at USTC a few years ago with bosons. Okay, so far for the tools. Now let me come to the main part, which is how to enhance the capabilities of quantum simulation in the broadest sense. And as I said, 2 things that we'd like to improve are how can we get more interesting states into our simulators, and the other part, how can we measure more interesting observables. Okay, and the sequence of events here is basically that we have some kind of Fermi gas, which is denoted here by bulk fermions. We load it in our simulator. Then we actually did a little trick here to get rid of single atoms by ramping the B field into a Feshbach molecule. Okay, it's not completely new, but it's quite nice for us because we can remove these single states that we have always these molecules next to empty sites of the lattice. So we have these, for example, 4 chain happening randomly in the lattice, also 2 chains, 6 chains, and we have these empty sites here. So this is our analog resource state. So we have many instances of these 4 chains where we have a singlet on side 1 and 2 and a singlet on side 3 and 4, and this is what we call CS, chained singlets. Okay, and then we use these 4 chains to do maybe some evolution, and at the end, the goal is to measure some correlation function. And here now is the moment where the third particle comes in. So we have now these singlets on double wells, and by merging the lattice site, we can read out the parity of the 2-particle wave function. So this is a little bit more powerful than just projecting into the Z basis, because this is pair symmetry selective. So if you have a singlet state, the spin wave function is antisymmetric, but the spatial wave function is symmetric, which means that if you merge these two atoms into a single well, they populate the ground band. And this ground band, then one can map if and only if it was in the singlets part to a third state. So the green ball here is kind of sorry that it's small, is the third component. So the number of green atoms shows the fraction of singlets in the system. If we had a triplet wave function, which is spin symmetric but spatially antisymmetric, this merging would lead to a higher band occupation, and our kind of conditional spin flip does not happen. So in this measurement, you can get correlators which are kind of fundamentally quantum, because you can kind of measure directly the singlet and the triplet part of a two-particle wave function. You don't rely on kind of assuming other things to find these correlations. Okay, of course, we can then also look at ZZ correlation functions, which are kind of the standard ones, which are then important for this project. Okay, so now let me walk through what we did with these states. So we have again this resource state of these singlet, 4-particle singlet chains. We can now measure this correlator, and we measure, let's say, on the strong bond. Here we find these correlators 1, 2, and 3, 4. Again, we have this singlet-triplet oscillation. If we had a quantum gas microscope, you would not even need this oscillation. You would just single shot read out singlet, triplet, up, up, down, down. But since we have average over a bulk system, we do this oscillation to basically read out the singlet and the triplet fractions as function of time. If we now measure on this bond here, we find consistent with 0 correlations, because obviously these singlets are isolated. Now we can use our pump. So this is kind of the first take home. We can use the pump to reshuffle atoms in the lattice before measuring. Okay. So if you wanted to measure a correlator between site 1 and 3, of course you can project into the magnetization basis and like look at long-range correlators. But here we get a correlator which is directly a quantum correlation between site 1 and 3 by reshuffling the atoms in a way to bring these two next to each other, and these two as well. And in the starting state that we had this singlet chain, again we have 0 correlation here, because these atoms are not correlated. They belong to separate singlets. And we can even go further and rearrange the atoms such that the 1-4 pair is moving together. And we have this 1-4 next nearest neighbor correlation function. So to prove that we can measure this, we now apply as one of our gates to the middle two atoms. So we have now this swap here, which is supposed to create a state which looks a bit peculiar. So we have this singlet correlation on not on nearest neighbors, but next nearest neighbors. So we have this kind of intertwined singlet state here. So if we now do our measurement scheme, we find 0 correlations here on both bonds, but we have strong correlations on these next nearest neighbor sites. So I think it's quite nice that we have this measurement toolbox now to read out non-local correlations, which could help for all sorts of things, maybe topological order or superconductivity or so, because very often you want these kind of long-range behaviors captured. Okay. So this is for the readout part. Now let's look at the states that we can engineer. To summarize the measurement, yes, our correlation, which was initially here, has kind of moved to 2 sites apart. Now let's go to the state preparation. So basically this part here, where using these gates, we can now entangle our singlets in a way that would not be possible if you just had the Hamiltonian evolution. And what kind of states can we make here? So the gate sequence we came up with, again, starts from this resource state, and then we have a kind of gate in the middle and 2 gates at the sides, at the edges. You might ask, why do we do 2? This is like a more technical reason, because we have to kind of collimate these atoms, because if we just did 1, these 1 and 4 atoms are actually pumped out. So they would not be anymore on neighboring sites, which would, for our measurement technique, not show up. That's why we kind of do this back, so this reversal here, And here you see why it's important to have empty lattice sites next to our chains, because the atoms can kind of propagate outwards and inwards. And now we don't do a swap gate here, but we actually do an entangling gate, or a kind of interpolation between a swap and an entangling gate, which is what we call swap to the alpha. So if alpha is 1, you swap the atoms, but it's not entangling. If the alpha is 0, you have identity gate. But if it's something in between, you can create correlations in your system. And this is plotted here on the x-axis. So we tune kind of the gate exponent alpha, and these are the data points, and this is a theory without free parameters, and we see that indeed the correlation, the antiferromagnetic correlation on these local singlets goes to 0 as we kind of change the state with these gates. And now we do our toolbox of measurements. So we look at this other bond correlator, and we see that during this circuit here, we indeed create correlations here, and we can also look at these non-local correlations, where we even create these ferromagnetic correlations for certain exponents, and also these long-range correlations. So the goal of this long-term, of course, is to create interesting states for quantum simulation, and we could show already here that our scheme allows to increase the overlap with the ground state of this actually Heisenberg model to above 99% in theory, to enhance basically our abilities. But not only that, we can, as I said, also create states. For example, this one here, you would never get just by kind of loading some atoms into your lattice and kind of doing some adiabatic evolution, because it's kind of non-trivial correlations here. Okay, so this is basically the main story that I wanted to tell you. Let me give some credit to my colleagues, collaborators. So Zidzir just graduated and took up a position at Fudan University. And the other work that I showed you was led by Jan Kiefer, postdoc, together with now Lars and Lisa. And the other team members are setting up the next generation experiments in the lab of Tilman Esslinger. Now, in the last minute or two, I'd like to advertise a few things. So I recently got a grant to start up my own research lab. So the goal is to build a universal quantum computer here. So not only having this swap to the alpha gates, but also single qubit gates and rearrangements to really get arbitrary connectivity here, also with fermionic degrees of freedom. So if you're interested in working in this direction, please let me know. And I'm starting my lab at ETH soon, so it's a very exciting time for me. And we also like to say that we're organizing a conference next year in August, Emerging Directions in Neutral Atom Quantum Information Science, together with Julian Leonard and Wen Chao Xu from PSI. So you're welcome to attend. And let me summarize what I told you today. So I think this topological pump, this kind of moving atoms through lattices, really is a kind of best of both worlds. You have like the kinetic part of moving atoms, but you also have the kind of qubit kind of language where atoms are not dispersing all the time, but remain localized. And using this, we realized these really high fidelity gates. I showed you how we can make progress in quantum simulation by engineering more non-trivial states in these systems, and long-term gave you my view on how we might build these more universal quantum machines in the future. So thank you very much for attending.
Questions?
So nice results, Konrad. So I have a very naive question. So how do you measure the fidelity in this setup?
Mm-hmm. Let me see whether I can. So we basically we repeat the gate many times and then fit a exponential decay. So this is what we get. So if we do like 30 gates, we have like a final state here, and we fit the exponential decay, and then we correct for example, atom loss, which is our dominating loss mechanism, and then that's how we get the 3 nines.
I have a question regarding the scalability of the problem if you want to be on a universal quantum computers. I mean, so you show us a 1D collision gate somehow, right?
Yeah.
Do you think you can go to 2 or even 3D?
Yeah, very good question. So I, of course, believe we have to go to 2D, maybe even 3D. I think in 2D, sorry, you can rephrase the question a little bit in a way of how to rearrange these atoms. So obviously, it's possible to do this structure in 2 dimensions. But the easiest way to think of it is that you have a collection of A sites, which are kind of stationary, and a collection of B sites, which are movement. And then you can think about how to rearrange these atoms. And what is very nice is that we, unlike the tweezer people, we can really, because of our swap gates, we can move through the atoms. So they are really moving physically through each other, which means that we save a lot of time, which would otherwise be wasted for avoiding all the other atoms. So this is something that's, I think, very promising. And scalability is also key here because our lattice sites are actually half a micron, so on the wavelength of the lattice, which is much smaller than the tweezer spacings because you fit roughly 10 times more qubits in the same area. So I think I'm very optimistic in terms of scalability.
Thanks a lot for the very nice talk. But somehow what we are saying is that if you add also a microscope, you could do what the tweezer dreamed to do, that to ensemble the perfect mode, right?
Mm-hmm. Yeah, this would be indeed one of the experiments I'd love to do, yeah, because you can think of, yeah, you have like some low density regions, you rearrange the atoms and you bring them together, yeah, that's, yeah, very exciting prospect, yeah.
Yes, very nice. But let me also come back to that. Also, the comparison to the tweezer system. I mean, the tweezer system also one advantage of your system certainly is that you're using light much more efficiently, right? That's certainly because for each tweezer atom you need whatever finite power certainly, and here you have a standing wave, right?
Yeah.
But in tweezer systems you can move all the tweezers around at the same time.
Yeah. Yeah.
And here you can, what do you think you can do? You can move one row and one column, but you cannot move all the atoms, let's say, in one row simultaneously, right?
Yeah, yeah.
Or you have to play some additional tricks.
Indeed. So we're kind of, that's, time will tell. So basically, as I see it, we have this moving array of B sites, which is kind of parallel moving, and then we have the stationary sites, and for some applications, it might be very efficient to do it in parallel, and for some others, it might be less efficient because you really want to move like 1 to 2, 1 to 3, 1 to 4. But one thing that is nice is that you can, without having to reverse direction, you can like move one atom across 4 atoms very kind of cheaply. So some of the routines of quantum computing might be very efficient, and then we'll see what overweighs in the end. But of course, yeah, we give up certain flexibility by not having the ability to move kind of completely arbitrarily relative to each other. Yeah.
Any more questions? So maybe I have.
Yeah.
You identify that you have effectively one atom every time, but you said in the experiment that you had 34,000 running at the same time. So which qubit then reads which gate?
Yeah.
This cartoon is a bit...
Yeah, this is very much the future. This is not what we're doing currently. What we're currently doing is you can think of a really kind of mesoscopic collection of double wells doing this gate operation. So everything is happening in parallel, and the number of fidelity I quote is averaged over all these atoms doing it in parallel. So I actually believe that the fidelity in the center of the trap is actually even higher, and that the end of the trap may be a little bit lower. But yeah, you have to really think of it as happening in parallel at the moment.
Another last one. If you would do then 3 tones and have 3 bands, so can you do funny 3 qubit gates?
Yes, that's a very good point. Yeah, so of course, if we look at the Hofstadter butterfly, so to speak, which you can map the topological pump to a certain degree, yeah, you can really think about churn numbers different from 1 and 0. You could have 2 and 1 and some atoms moving twice as fast. So actually, it's something I never really thought of, but that's a very nice, very nice idea. Yeah.
So if there are no more questions, let's thank Konrad.
Thank you.